Let's have some fun today. Okay, so today, this is our lecture number 12, if I'm not mistaken. So we are completing 6 weeks here. We are going to talk a little bit about Fubini's theorem. Okay. But first, let me do a brief review on what we did last class. Last class, we discussed a little bit about the Radon-Nikodym theorem. And if you remember, I think the setup was like this. So you have, say, a measure space. You have nu being a signed measure on a certain, say, measurable space, and mu being a sigma finite measure, non-negative measure. Okay, let me see if I just got this correct. So I have no paper today. I have to look at my virtual notes here. Let me see what I wanted to show. So the idea was that, first one, that there is a unique way to decompose this nu as a sum of two measures, nu A and nu singular, nu A being absolutely continuous with respect to mu, and nu singular being mutually singular with respect to mu, and this decomposition is unique, and the absolutely continuous part, so meaning there exists a unique function h in L1 of mu, such that nu, the absolutely continuous part, is just the integral of h with respect in this set E. Okay. So this was the Radon-Nikodym theorem, Lebesgue-Radon-Nikodym theorem. Radon-Nikodym theorem is usually refers to the second part, that if I give you a measure that is absolutely continuous with respect to a non-negative and sigma finite measure, then it's given by an integral of an L1 function. Okay? First part says that if you give me any sign measure, I can decompose in a part which is absolutely continuous and in a part which is mutually singular to the given mu measure there. Okay? This decomposition is unique. I wanted just to highlight as maybe a corollary this, or a theorem, a version prime. Okay. What's the situation when you have two, let's say two sigma finite measures on sigma. Let's just think about now the situation of mu and nu being sigma finite on this measurable space. Okay, so sigma finite. Now, the two of them being sigma finite, no negative measures in the classical sense. Okay. So the only difference is now this measure nu may be infinity. Okay, but I'm assuming that it's sigma finite. So the claim is that you still can do the decomposition. Nu equals to nu A plus nu S. Nu A absolutely continuous with respect to mu, and nu S mutually singular with respect to mu. And now I'm going to say that there exists a non-negative and measurable function h, such that nu a of e is equal to the integral of h d mu over e. This h here is going to be, say, locally integrable. I'm putting locally here in quotes because we may be in a very general measure space. We're not in RD, okay? So locally, in principle, there's no neighborhood of points. I mean, this is just a... but we will see in the proof. So let's see. If we wanted to prove this theorem, if we have this one in mind. So I have a theorem where I can decompose a signed measure. My measure could even have positive and negative signs in a sum of two. One the absolutely continuous part and one singular part. You realize that this is a linear thing. So in the proof, if you remember, we actually just considered the case where nu was non-negative, but finite. Okay? Being finite was important to do this, to get the function which is in L1. Now we are in a situation where nu, my measure nu, is still non-negative, but it's not finite anymore. It's just sigma finite. Okay? So what could we do? Well, what you could do is you could say, you could certainly write your space as a union of sets, Kn, let's say such that can take this unions of Kn such that nu of Kn are all finite and mu of Kn are all finite. Can I do that if I want? I can certainly do it for the two measures separately, right? I can certainly write my whole space as a union of ANs, where nu of AN is finite. And I can certainly write my omega as the union of BJs, where mu of BJs are finite, because I'm assuming that both measures are sigma finite. I can take intersections here. So I can write this union to AN intersection BJs over N and J. This is still a countable union, and now both of the measures will be finite in the set. Okay, so I'm okay. I can write this as a union of Kn such that both measures are finite. I can go further in this construction and take, whenever you have, you can also assume that the Kns are disjoint. Okay? Because if not, if you have a union of certain Kns, what you do is that you take K1, and then for the next one, you take K1 tilde to be K1, you take K2 tilde to be K2 minus K1, you take K3 tilde to be K3 minus the union of the previous guys, and keep doing this. Okay, so you keep at each step, so you take this to be K1, and you take this to be K2, and then if you have a K3 here, you just take the new part. So at this, you can construct disjoint sets K tilde such that the union of K tilde from 1 up to N is the same from 1 up to big N for any big N. Okay? All right. And since these Kn tildes in the construction are subsets of the Kn, the property that the measure is finite keeps being preserved. Okay. So you can, in fact, write your omega as a union of sets Kn, where both measures are finite, and these Kns are disjoint. Very good. So now you consider the measure nu n to be just nu n of a set E to be just nu of a set E intersection this Kn. Okay, so here's your space. Here's your omega. You split in K1 And then you have here K2. K2 is just this piece. Okay. And then you have here K3, which is just this piece here, so on. So you split your measure, you consider this measure nu n to be defined as nu of E intersection Kn. Now, this is a measure, you're putting yourself in the previous situation. Now, this is a finite measure, okay? So you can certainly write nu n as a nu n absolutely continuous part plus a nu n singular part, okay? With nu n absolutely continuous with respect to mu, and nu n singular with respect to mu. This, the composition of the measure nu n is unique. Moreover, this nu n absolutely continuous part is equal to the integral over the whole space, if you want, of a certain function hn d mu, okay, where this hn belongs to L1 of mu. But notice that since the nu n is supported in Kn, this function hn here has to have, the support of hn has to be contained in Kn. In other words, if this hn had some points, the set where the hn is different from 0, this is the set of where hn is different from 0. That's the support. It's containing Kn. Well, this is I don't care about sets of measures 0, okay? There's no topology here, okay? So this, I can say that this hn is different from 0 is contained in Kn, because if it has a set where it's different from 0, a measure non-zero outside of Kn, I would break this, okay? In other words, the set where hn is different from 0, intersection Kn, the measure of this has to be 0. This is what I mean when I say that the support is contained in Kn. Okay? So this function hn is a function in L1 of mu and has support in Kn. So is this measure has support in Kn, and this measure has support in Kn. Okay? So I think now that the idea is to just add all these things, you know. The idea, since the Kns are disjoint, is to just consider a measure nu A to be the sum of nu A absolutely continuous part, nu S to be the sum of nu n S in n, and the function h that you're seeking to be the sum of hns over n. Okay? That this is a measure because you just add in a countable, well, you can check that this is a measure just that this is countably additive, because each of these are, and they have disjoint supports, right? So what I mean here is that nu A of E will be the sums of nu n A of E. Yeah. So it's clearly that if you have a, well, it's a countable sum of measures. It's clear that if you have if you take nu A of the union of these joint sets EJ, this is the sum in n of nu A of the union of EJs. Each of these is a measure, so you get a sum in n and a sum in j of nu n A of EJ. Now what you do is you reverse, right? These are all positive numbers. So you get sum in j of this one that you call nu A of EJ. So you get countably additivity. You get that the measure of the empty set is 0. So this is a measure, this is a measure. If each of these is absolutely continuous with respect to the measure mu, then if mu of a set E is 0, all of these are 0, therefore nu A of the set E is 0. So this nu A that you created here is also absolutely continuous with respect to mu. If each of these is singular with respect to mu, it means that they live in a place and mu lives in another place. So when you take the sum in n, the sum of these measures lives in the union where all of these lived, whereas the mu lives in the intersection of all of these sets, and these are still disjoint. So the sum of singular measures is going to be singular. Okay. Finally, this function h, which is the sum of hn, you would like to verify that this thing here goes to a limit, you know. When you have nu A of a set E, well, this is nu A of E equals to the integral of h. Right? You would like to conclude that this is equal to this. Okay? This is just an application of the monotone convergence theorem. Okay? Nu A of E is the sum of nu A n of E in E. Each of these is the sum, is the integral of over E of function hn du, if you want, which is the sum of, if you want to integrate in omega, of hn characteristic function of E, the mu. Okay, so maybe it's better if you write this as the limit when big N goes to infinity from n1 to big N. You keep writing here. This is the limit when big N goes to infinity. Little n goes to 1 to big N. This is the limit when big N goes to infinity. Little n from 1 to n. At this point here, you can change. This is the limit when n goes to infinity. The integral of this, the sum of hn, since this is just a finite sum. Characteristic of E, d mu. And here you have non-negative functions who monotonically increase to a function that you just called h. It's not necessarily integrable. It's certainly non-negative and measurable, like we're claiming here. Okay? And this we know by the monotone convergence. That this is just the integral in omega of h d mu. Okay, so this concludes. So you really construct the function h, which is the sum of these functions hn at each step. Each hn is supported in this set. So we have one function supported here, have another one supported here. So therefore, if you take in any of these sets, your function h will be in L1. When I say it's locally integrable, I mean that it belongs to L1 of each of these guys, Kn. Okay? In your covering the space. So it's locally integrable in this sense, but it does not necessarily belong to L1 of the space. Okay, so this is what you can do in general, you know, by. Is that clear? So in the homework for this week, I have assigned maybe 1 or 2 exercises where you have a couple of measures and you have to find the Radon-Nikodym decomposition of one measure with respect to the other one. Are you having fun with those exercises? Good, huh? Or not so? Okay. So I am going to give to you today the updated version of our notes for the course, you know. So these notes are essentially an outline of what I have been trying to do here. Of course, you can study by these notes. I'm trying to make them, you know, try to make them self-contained. But some of the easy details I'm skipping, so I'm leaving some details for you guys as readers to fill out. I mean, some are easy, some are not so easy, but they are just routine. So if you want to study by these notes, only by these notes, that's fine. But I would also encourage you to reach to your favorite books and read the favorite books on each subject as well, okay? So I'm going to give you today the updated version of the notes with up to today's class, up to Fubini's theorem. Especially because it contains some things that I was not able to talk here in class due to time constraints, you know. For example, with the Radon-Nikodym theorem, you can prove that the Rees representation theorem in general. Okay, so theorem, sometimes we call this the Rees representation as well. In the sense that if 1 is less than or equal than p is less than infinity, then LP dual is equal to LP prime. 1 over p prime is equal to 1. Okay, so let's assume here that my measure mu is sigma finite, okay? Maybe you might need more, but let's just stick with this. Finite and complete, if you want. But this is a nice statement that the dual of LP, so any bounded linear function in LP is given by, so in other words, any bounded linear function in LP, so remember, L was a bounded linear function in LP if it satisfies this thing. So L of f was less than a certain constant times the norm of f in LP, okay? Norm of L. So these are the bounded linear functions. Bounded linear functionals. I assigned to you an exercise to show that if you have a normed vector space, you always have a space of bounded linear functions on that normed vector space. And this is a Banach space. Well, in principle, it could be trivial. It could be just that you had just the zero functional that assigns to each element in your normed vector space the value 0. To actually prove that the space of bounded linear functionals is non-empty, technically, you need the Harmonic Theorem. This is something that you will see in your functional analysis class, functional analysis course, I suppose in the first class or in the very beginning of the course. But for example, when you are working in LP, there is a lot of functionals in LP that you already know. So if you take the map, let's say if function g belongs to LP prime, and then you take the map that sends f to the integral of fg, okay, this is a bounded linear functional. It takes a function in LP and maps into a number, okay? I mean, you can be working with real valued or complex valued functions, that's fine. And it maps to a number because of Holder's inequality. You have the bound that you want, because this loses to the, you know, to the LP prime norm of G times the LP norm of F. So this is a number that loses to a certain constant. Your G is fixed times the norm of F. Okay? So multiplication, I mean, if you integrate F against a function in LP prime, you get a bounded linear functional in LP. And this theorem here says that this is the only way of doing this. So all the bounded linear functionals in LP are of this form. The same way that we had in L2. In a Hilbert space, the bounded linear functionals are always given by an inner product with an element of the space. This is the case, for example, of L2 here. Okay? But in LP, when p is between 1 and not infinity, but infinity is a little bit different, it's a little bit more complicated case. The dual of L infinity is not L1. It's some space that is bigger than L1. It's a space of, certain space of measures. But we won't talk too much about this. Yeah. Okay, so I will leave to you in the notes to read the proof of this result, which is also very nice and uses, I mean, there are different ways to prove this result, but the one that I wrote to you uses the Radon-Nikodym theorem to generate, this right candidate function here. It's a very beautiful proof. And there are some other corollaries of the Radon-Nikodym theorem and some nice propositions that I want you to see in the notes, okay? One of them, actually, I assigned to you as an exercise in the homework last week, in the sense that if you have an integrable function, if a measure is absolutely continuous with another measure, for any delta, for any epsilon, you can find a delta such that if the measure here, this set is less than delta, then this measure of this set is less than epsilon. Yes. Okay? So take a look at these propositions, read the material that I'm going to send to you. This is everything I wanted to do in the last class, plus all the things that I didn't write. So you guys see what I wanted to tell you, but the time is not enough. Or maybe I mismanaged my time. I don't know. Maybe it's a combination of both. Okay. But I hope the exposition on the Lebesgue-Radon-Nikodym theorem was nice. It's a nice theorem, especially one of my, I have listed in the bibliography of the course, I don't know if I listed this in the beginning, but in the bibliography of the course, in the bibliography of the notes, in the references, I listed some of my favorite books in real analysis. And one of my very favorite books in real analysis is the one by Rudin. I don't know if you know this book by Walter Rudin, called Real and Complex Analysis. It's really a nice book. It's not an easy book. It has some very, deep. Yes. So you can see why I would identify myself to that book, because this is sort of stuff that I would like to do, short but hard, where you have to sit down and think about, and this is how you learn, Rudin's book is very, very nice book. And in particular, I got this part I wrote about the Riesz representation theorem in Hilbert space. I got from Rudin's book. I like the way that he does. There are some very, very complicated problems in that book. Well, I remember when I was taking this course, when I was at your age, I was taking this course. I was mainly studying by Rudin's book. And I wanted to solve all the problems in the book, And I started solving and so on. But there was a couple of problems, I don't remember which, but very complicated. I tried all that I knew, all the constructions, It was one of these crazy counterexamples to construct something that converges in a way and doesn't converge in another way and so on. I could not do it at all. But once I wrote to Rudin, I checked online if he was an emeritus professor at the University of, I guess, Washington, Seattle or something like this. He was still alive. I don't know if he's still alive or not. But I wrote to him an email with this one problem that I was trying, Hey, professor, I'm reading your book, I'm stuck in this problem. I don't know how to solve. Could you give me a hint? It was just a generic problem, section 7, problem 7.8. And then he wrote me, he replied. I was very glad that in a few days he replied. The guy was not only, was retired, but he was active. So he replied to me and said, hey, thanks, I'm very glad that you're interested in my book, blah, blah, blah. This problem, I think you can solve it like this. And he gave me a suggestion. And this was one of the things that I had tried. And I said, hey, professor, I don't think this works because of this, this, this. I tried this idea. And then he wrote to me again, oh, yes, you're right. This doesn't work. But I think this thing works. And then he gave me another idea, which I had already tried as well. And then I wrote to him and said, I was a young guy. I didn't know how to say that. Hey, professor, I'm sorry, but I don't think this works too. And when I've tried, I cannot understand why it works and so on because of this counterexample. And he replied to me, yes, you're right. This doesn't work. Yes, I don't think I know how to solve this problem. And this ended up our communications in the email. If you happen to solve the problem, please let me know. I guess I found the solution on the internet maybe a few months later, I could never solve the problem, but I found a solution. And it was beautiful, yes, it was a beautiful solution. So now I want to move our discussion to discuss Fubini's theorem. Fubini's theorem, as you might already know, and you might have already used it several times in your life, is the theorem that says that you can switch integrals. Okay? You can have a double integral, and you can switch. You can do the integration in the order that you prefer, okay? In the order that it pleases you. Now, there are some technical, interesting stuff about Fubini's theorem that I want to discuss with you separately. So first, I want to do the case where we have the Lebesgue measure. Okay? First, I want to do with you the case where we are working with the Lebesgue measure. Let me see if I can just do one thing here. System preferences. I don't want to go to sleep. Okay. That's fine. I want to do first the case when we are in the Euclidean space. And then move to a general case. And I want you guys to understand the difficulty. In the Euclidean space, in RD, okay, if I write my RD as 2 as the product of 2 guys, so I'm going to write RD as RD1 times RD2. In other words, I'm going to take a points in RD, I will denote by x, y, where x belongs to RD1, and y belongs to RD2. Okay? So in the Euclidean space RD, we already constructed a measure, which we call the Lebesgue measure, in each of these guys. So we already have a measure here, and a measure here. Okay? And we're going to have a discussion on Fubini's theorem, how can I change the integrals, but the spaces and the measures are already given in each of the spaces. Okay? We already constructed that. There's a second situation where you have a general measure spaces. When you have 2 measure spaces, when you have, say, a measure space omega 1 with a sigma algebra sigma 1 and a measure mu 1, and you have another space omega 2 with a sigma algebra sigma 2 and a measure mu 2, you want to construct the product space. The product space is going to be omega 1 times omega 2. This will be made by the points x, y, where x belongs to omega 1 and y belongs to omega 2. That's fine. Okay? But I'm giving you a sigma algebra on omega 1, and I'm giving you a sigma algebra on omega 2. So the first question here that you have to address is, how do I construct an appropriate sigma algebra on omega 1 times omega 2 on this product space? Okay? So this is, and how do you construct a measure? Once you construct the appropriate sigma algebra, how do you construct a measure on such sigma algebra? Okay? So these are questions that you have to address. Okay? In a nutshell, we're going to come back to this, but I can tell you in 3 minutes what's going to be the answer. Well, the sigma algebra that you want, what would you like to happen, you know? If you have a set A here, if A is a measurable set, if A belongs to the sigma algebra 1, and B is a set in the sigma algebra 2, then it's reasonable to ask that A times B belongs to the sigma algebra that we want to construct. Okay? So I want products of sets to belong to the sigma algebra in the product space. And I'm going to call this, generically speaking, a rectangle. So a rectangle in the product space will be a product of one thing here times another one there. This is going to be a generalized rectangle in the product space. And the sigma algebra that we want to construct is going to be the smallest sigma algebra generated by the rectangles. Okay? So it's the smallest sigma algebra generated by these sets. So you have a bunch of sets. You want them to be measurable. So you have to construct the smallest sigma algebra that contains them. And how about the measure? Well, the measure, mu, that sometimes you denote mu1 times mu2. So the product measure, you want the product measure on a rectangle to be what? You want the product measure of a rectangle to be the product of the measures of each of the components. So you want this, okay? So your goal now is to prove that, okay, but then you have just defined the measure on the rectangles. So your goal is to prove that you can actually have a measure on this sigma algebra that is much bigger than just the rectangles. It's the smallest sigma algebra that contains all the rectangles. So you have countable unions, intersections, and whatever, complements. And you want to show that this measure that you constructed just in the rectangles can be extended to a measure in the sigma algebra. Okay? And in fact, if the measures that you start are sigma finite, if this is a sigma finite measure and this is a sigma finite measure, then there will be a unique extension to the whole sigma algebra of sigma there. Okay? But to prove that there is such an extension, it's not so easy. You really have to start with, you really have to appeal to the Carneiro-Theodorus theorem that I have it in your notes too. This is a class that I decided to construct the Lebesgue measure in a different way, but I wrote down to you, so you have to read the theory on that section of the notes that I didn't give a lecture on, about the Carneiro-Theodorus theorem, about pre-measures, about algebras, okay? So the routine here would follow that, because you will construct first, starting from the rectangle, you will take just finite unions, finite, let's say, disjoint unions of rectangles. Okay. You take finite disjoint unions of rectangles, and you call this A. Well, finite disjoint unions is the same thing as just take finite unions of rectangles. Because if you take just two rectangles, you can decompose the rectangles into smaller pieces. Okay? But finite unions of rectangles, this is going to be an algebra. You have to prove that this is going to be an algebra in the sense of the notes, you know. In the sense that, well, if you take complements, it will still be here. And if you take finite unions of guys here, it will still be here. So finite unions of finite disjoint unions of rectangles is still going to be a finite disjoint unions of rectangles, if you want. Okay? So this is going to be an algebra. And you have to prove that you can define a measure mu here. So you will define the measure mu in A and prove that this is going to be a pre-measure. So this is going to be an algebra. This is going to be a pre-measure on this algebra. And then you will appeal to the Carneiro-Theodorus theorem. Whenever you have a pre-measure on an algebra, this measure extends to a measure in the smallest sigma algebra containing this algebra. Okay, this is what you get the construction here. In general, and then you can prove, as I'll give to you on the notes, then you can prove Fubini's theorem in this product space with this sigma algebra with this measure. In general, the thing that you construct, the product space with this sigma algebra, with this measure, in general, you don't get a complete measure. Okay, even if you start with complete measures, you don't get a complete measure here to start with. But you can, of course, complete the measure, as you also have solved in one exercise. You can complete the sigma algebra, and you can complete the measure. And then you can still prove Fubini's theorem in this completed space. Okay? So if you were to start like this and prove it, say, on R2, you would start with Lebesgue measure. You would construct the product sigma algebra, which is not yet the Lebesgue sigma algebra in R2, but you can complete what you want. Okay? So there are two different ways of doing this. I'm writing to you in the notes that I'm going to send to you later, these two approaches. Okay? First, it's nice to do it in the Euclidean space because this is mostly what we care about in this course, where you already have the measures here, here, and here. But also it's very insightful. Sometimes you'll be working with dynamical systems, probability. You have to know, if you have two spaces, what is the product sigma algebra, what is the product measure by definition, you know, and how Fubini's theorem applies. Okay? So then next step would be extend using Carneiro-Theodorus theorem. Okay, so here essentially is the outline. Okay. Let's focus our discussion for now in the Euclidean space. Because the proof is relatively similar. You know, the proof that you get in the Euclidean space and the proof with this outline is relatively similar. You will need these ingredients from before to actually define the sigma algebra and define the measure in the sigma algebra. So you need these three things to learn about what an algebra of sets is, what a pre-measure on an algebra is, and how can you extend the pre-measure to make it a measure in the smallest sigma algebra that contains that algebra. The sigma algebra, yes. Yes, you get a measure, the Carneiro-Theodorus theorem gives you a measure on a big sigma algebra, the Carneiro-Theodorus measurable functions, right? The sigma algebra is usually bigger than the smallest sigma algebra generated by that algebra, okay? I'm not so sure if it's the completion of this thing, this measure. Then I have to think about it a little bit. The Carneiro-Theodorus thing might be still a little bit bigger. But I'm not sure. Same as the completion, right? Okay. Yeah. I would have to check that, but it's plausible. It makes sense. Let's see. Let's try to have a discussion on RD. And I let you guys read about this at home. Fubini's theorem, as many of the theorems in this course, is something that you have to sit down and read the proof once in your life and understand. Make sure you understand. Once you have done that, then it's the time to forever and ever learn how to use it. Okay? Okay. Okay, so let's have the the setup in the Euclidean space. Let's discuss how we would do that. The idea here would be, again, let's write my points in RD. Let's write RD as RD1 cross RD2. Okay. Let's write points in the form XY, where X will always belong to RD1 and Y will always belong to RD2. Let's call the Lebesgue measure the Lebesgue measure is going to be called M. I'm not going to put M RD1. M, whenever it appears, obviously you understand that's the Lebesgue measure in this space, or in this space. Okay, so for F, let's say for F, take real valued functions. If you have a measurable function in RD, let's define the slices. We define the slices. I'm going to define the slice F. Let me just adjust so I can get my notation like I have here. I'm going to define the slices Fy of x just being f of, right? So this is a function of x, and fx of y will be just f of xy as well, okay? So in one thing, you fix y, and you get a function of x, just looking at the first variable, okay? These are the same as the map that sends y to f of xy for x fixed, okay? But I'm just calling this map f superscript y. And this other one I call f subscript, subscript x. So these are going to be called my slices. Okay. Now, similarly, if you have a set E contained in RD, a measurable set, Lebesgue measurable set, you define the slices EY. EY is going to be the set of points X in RD1 such that XY belongs to E. And the slice EX is going to be the set of points Y in RD2 such that XY belongs to E. These are essentially this construction with the F being the characteristic function of the set E. So now let's see what we want to prove. So theorem will be, let's state Fubini's theorem in this form. This is going to be our goal for the next 40 minutes. Okay. Suppose that a function, certain function f of xy here is integrable in RD. Okay? So I'm starting with a function that is integrable in RD. Then, for almost every y in RD2, we have first the slice function, the function Fy is measurable, is actually integrable, in RD1. Whenever I say that a function is integrable, I'm implying that it's measurable, okay? So you start with a function which is integrable in RD for almost every, and of course, the measure here is always the Lebesgue measure. For almost every y in RD2, we have that the function, the slice function f sup y, is integrable in RD1. The function that sends x to the integral that sends y to the integral of fy of x dx in RD1. So this is a function. I'm sending y. So this function is integrable. So I can integrate, and I get the number. The function that sends y to this number is integrable in RD2. And third conclusion is that this, and the third one is that, well, if you now integrate over RD2, this function, integral over RD1 of fy of x, fy of x is just dx, and then integrate dy, you get the original integral of f in RD. Okay? So, let's see. A basic remark is that, of course, this statement is symmetric between y and x. So I chose to do it for y, but you could have chosen to do for x. So the thing is that, well, if you just integrate in RD2 and then integrate in RD1, this function here, fy of x, which is simply the original function, f of xy, you integrate first in x, and then in y. This is the same as integrating first in RD1 and integrating in RD2, f of xy dy dx, which is the integral of f. And everything is finite because you're assuming in the beginning that f is integrable. So, okay, so I'm assuming part of the assumptions in the beginning that f is integrable. Okay. How do we prove this? Proof. So you see, the idea of how would you prove this theorem? If I tell you, what would be your idea to prove a theorem like this? See, in many of these results in analysis, theorems, propositions, exercises in the homework that you have to prove, you have to sometimes start from the beginning, start from the trivial situations and build up. So the idea here is not to take a function which is integrable right in the beginning. This will actually be the last step. So we are going to try to reduce our problem to see what's the core issue here. Okay? Yes. Okay? So I'm first going to try to see if the situation is okay for a cube. Characteristic function of a cube should be okay. If I can take linear combinations of functions, that would be okay too. Okay, if I can take limits of functions, if that would be okay too. And then I start to see what are the conditions, and in some point we'll eventually end up having to prove this theorem just for characteristic functions of sets. Okay? You have to use these approximation results that you know. Okay, so let's divide the proof in a few steps, and let's do it together. Okay, so what do I want to do first? So, okay, so let's call it, let's call it F here, the class of integrable functions in RD that verify conditions 1, 2, and 3 above. Okay, I'm calling F, let's say, in principle, the subclass of the integrable functions that verify these conditions 1, 2, and 3. I know there are functions that verify these conditions. If you take the function to be identically 0, certainly verifies this condition here. Let F be the class of functions that verify these conditions, 1, 2, and 3, that I stated there. We are going to show that some functions belong to this class F, and eventually we want to show that this class F is the whole class of integrable functions. Okay? So let's try to do it in different steps. So let's say the first step would be, linearity. I'm going to say to you that this class F is closed under linear combinations. Under finite linear combinations, okay? Under finite. F is closed under finite linear combinations. So if you take F1, F2, Fk in F, sum of Aj, Fj also belongs to F. That is essentially clear from the statements, right? Because if you take k functions, if you take a finite number of functions that verify these three conditions, then each of the functions has a set of measure 0 for y where it does not hold, the results do not hold, right? You just take the union of these sets. Finite union of sets of measure 0 is still of measure 0. So in the complement of this set, everything works fine, and all of these things you can add up, right? If each of the function is integrable, linear combination is going to be integrable. Same here, and in the integral in the end, the integral adds up. Okay? It's not hard to prove, verify the details of this, that you can take linear combination of things that verify these properties. Okay, I should not say verify conditions 1, 2, and 3. I should say verify the theorem, because actually it verifies this for almost every y. So you should verify the theorem. That clear? That was a pretty fast step 1. So what else do I have? Step 2. Now, let's see. I want to claim to you the following. That this thing is closed under monotone convergence. Now, this is already going to be a big step. Okay? So, first was linearity. Second one is monotone convergence. Since that if you have a sequence Fk belonging to this class F, such that Fk converges to F monotonically, and by monotonically, I mean it could be decreasing or increasing, and your function f is integrable this limiting function f will belong to the class f. Okay? So you have a sequence of functions in your family, in this class where the theorem works, that converges monotonically to a function f. This monotone convergence could be a monotonically increasing convergence or a monotonically decreasing convergence. Pointwise, of course. Okay? And this limiting function is integrable. I claim to you that this function should belong to the family. Let's try to do this. Now, proof of the second step. Okay, so the first observation is that I want my convergence to be increasing in the classical sense. Okay, so by changing fk to minus fk, okay, I could change fk by the sequence minus fk, we can assume that the convergence is actually increasing. Fk converges to f increasing. Let's denote it like this. Converge monotonically increasing to f. Otherwise, if it's a decreasing convergence, you change fk by minus fk and work with that. Minus fk, you already know that it's in the business because it's closed under finite linear combination. Implies multiplying by minus 1 is a finite linear combination. Also, now you have a monotonically increasing sequence. You can subtract f1, the first function, from both sides. So fk minus f1 converges to f minus f1. And this is going to be a non-negative function because fk was bigger than f1. So we can assume also, that all fk's are non-negative. Okay, so let's assume that the convergence is monotonically increasing and that all the fk's are non-negative. Now let's get to business. Okay? Now you see how the monotone convergence theorem wants to appear here. How do we do that? Well, first of all, you have that the theorem holds for all these fk's. Okay? For each function, for each of these fk's, there is a set of measure 0 of such y's where the theorem, the things may not hold. So first thing that you have to do is to remove. Okay, so let's say nk, the set of y's in R2, such that one, two, or three, such that the theorem does not hold for fk. So let n, so this, the measure of each of these guys, the Lebesgue measure of each of these guys is 0. Because I'm saying that the theorem holds almost everywhere. So then, first thing that you do is you take n to be the union of all these nk's. You still have a set of measure 0. Okay? So now take y does not belong into this n. So this is the bad set, the set where it does not hold. The bad set has measure 0. Take a guy that doesn't belong to this set. Tell me, Walter. Problems?
Yes. Part of the blackboard?
Sure, I can do that. From here? Okay, good. Take a point that does not belong to this bad set. So then everything works up to that point, right? So then, let's see. So let's try to conclude. So then, this implies that each fk y, if you fix this y, this fky is integrable. In particular, measurable. Right? And this implies that the limit, since fky converges up to the function fy, this already gives me that the function fy is a measurable function. This implies that then this function fy is measurable. Moreover, these integrals converge, right? So the integral of this fy of x, the x, the integral in R d1, this converges to the integral of fy x dx in R d1. Number converges to this number by monotone convergence, right? So you have here your fixed y. So this is a monotonically increasing. All of these numbers are finite. They converge then. Fk of y converges to a function f that you call fy. Well, that is your fy. I'm also going to assume that the convergence. Okay, so maybe I should also say that. Okay, I'm also assuming that the convergence takes care pointwise everywhere at this point, right? Okay, I'm assuming that the convergence is pointwise everywhere. Let's see. So you have this because these functions are converging to this function. So these integrals are converging to these integrals by the monotone convergence theorem. Monotone convergence. At this point, this integral might be infinity. Okay? That's okay. Monotone convergence. As k goes to infinity. But again, you have these functions. So this is now a function of y. By the part 2, this function of y here converges to this function of y here. This function of y this is an integrable function of y by part 2. In particular, it's a measurable function. So you have an integral. This is a function of y. Y maps to this. Okay. This function of y converges monotonically to this function of y here. So it's a monotone convergence. Okay. In particular, this implies that the map, since y to this thing here, Rd1, fyx dx is also measurable. And another application of the monotone convergence theorem, the monotone convergence theorem, again, you get that this function of y here converges pointwise to this function of y here. In monotone, this is monotonically increasing because fk is monotonically increasing and non-negative. Therefore, if you integrate now over Rd2, it will converge to the integral over Rd2 of this. These are finite numbers that will converge to this number, which could be infinity. Okay? But let's see. Okay. On the other hand, this number here, you know, I use this, now I have to use number 3. I already know that for each fk, this number is the integral in Rd of fk in the two variables. Okay? And this, by the monotone convergence theorem, converges, another application of the monotone convergence theorem here, converges to the integral in Rd of f. And this thing here, I am assuming, it's part of the assumption of step 2, that this f is integrable. I have to assume this. Okay? So if this is finite, okay, then you conclude everything here. So then if this is finite, then this is finite. Okay? In particular, this function here inside, this function of y, is an integrable function of y. In particular, it is finite almost everywhere. Okay? Because it's integrable. So this function here is inside is integrable. In particular, it's finite almost everywhere. So there is a set of y that it could be infinity. You throw them out as well. And then you come back here, and you will have that. So this is part. So maybe I should write this. Okay. So this implies that the integral in R d2, the integral in R d1 of fy of x dx equal to the integral of f in R d, which is finite. So this implies that this function here, this thing inside R d1 fyx dx, this is finite for almost every y in R d2. Okay. So this is statement 2, that this function here will be, well, this function here is integrable in R d2. That is now step 2. And I guess that I have to prove step 1, that the function fy is integrable in R d1. But this is to say that this is finite, right? So I have to throw this out. So suppose you have another set here, M, of measure 0, the bad set. So now you consider, on top of this n that you threw away, you let the new n tilde to be your n, and you take this M. There's still a set of measure 0. Okay. And then for y not belonging to this n tilde, you had all that you had before, but you also had that this thing here is finite, which is to say that the function fy is integrable. Okay? So now, you do it reverse engineer, right? So you start with this n, take this union of this with this m here. For any y that's not in this set of measure 0, you have that your limiting function f is such that you already know that fy, the slice fy, was measurable, but you know that it's also integrable because of this. The map that sends y to this guy is integrable, and this is part 2, and part 3 says that this is equal to this because, because of this relation here. This is equal to this converges to this, and this converges to this, so both limits have to be the same. Okay, so this is how you prove this step 2. Okay, step 2 is done. Is that okay? So our class is closed under monotone convergence sequences, up or down, provided that the limiting function is an integrable function, that we ask that. Good. Need a bit of water. Now, after that, now we are going to try to start working now with simple functions. Okay, so the idea would be to, what are we missing here? So we have already seen that we are almost there. So maybe I think this was the most complicated step I have linear combinations is fine. I have monotone convergence is fine. Okay. Now this space is linear. So if this thing here is linear in the sense that if I start with an integrable function, I can take its positive part and its negative part. It suffices to prove for each of them independently, and then I can just add them up and get the result. So I can assume that my integrable function that I start is non-negative. Now, you could construct a sequence of simple functions that converges monotonically increasingly to this non-negative integrable function. So if I can prove for any of these simple functions, I will be done. But to prove for a simple function, which is a finite linear combinations of characteristic functions of sets, I just need to prove for the characteristic function of one set. So now let's try to prove that. Okay? Let's try to prove the statement for the characteristic function of one set. Now, sets, Lebesgue measurable sets, could be a little bit complicated. So let's try to prove for the easy sets first. So let me just say, okay, so let me prove this. So step 3 would be now to prove for sets. But we are not going to go directly for a measurable set. We are going to try to let's try to do an intermediary step. So step 3, tell me. I guess he said not here, no? Not here and not there. I guess he takes everything. Okay, so let me go there. Thank you. I'm not going to write here. The camera is not moving, yes, so maybe I should just write in these two parts. Okay. Well, I guess posterity will have to live just with a half board on Fubini's theorem. Let's see. Step 3. If my set E is a, what do I want? A countable union or a countable intersection of open sets? Countable intersection of open sets if E is a countable intersection of open sets, we call this a G delta set. It's a countable intersection of open sets with measure of E finite, then the characteristic function of E, measure of E has to be finite so that this is integrable. Characteristic function of E belongs to my class. Let's see how we do this. So, yes. So I want to do, what I want to propose to you is that we do it in the following way. Let me see. Okay, so let me do it. Okay, sorry. If my set is a countable intersection of open sets, then I'm okay. So let me divide this into very basic statements. So first one is that if my set E is a cube, if E is a cube, an open cube, okay, you can check that the statement holds. Okay. Okay. So check the statement if you are in an open cube. So if you have in an open cube, these slices will just be empty, or it will be a lower dimensional cube. Therefore, these things will hold. So you can check that. The second step open, let's say open cube. Then I say it's okay. Check. Second statement is that if E is contained in the boundary of a cube, cubes in RD2, okay? RD, sorry. If E is contained in the boundary of the cube, of a cube in RD, then the result also holds. You can always check all the possibilities here. In this sense, the function will just be the slices of E, or it will be empty, or it will be a set of, I mean, for almost all Y, it will be empty. It will have measure 0 if E is contained in the boundary of a cube. That makes sense, right? I'm telling you that this holds, in the sense that suppose you are in 2 dimensions and your set E is contained in the boundary of the cube. Suppose it's some set here, lies here and then here. And you want, say, to project on this space, okay? So let's see, we want the Fy, so the set of X, yes. Suppose this is the X, this is the Y. You have a picture like this, okay? So suppose this is your function, just some open set here, and you want to project. So the Fy's here would be just the, what are the X that, for each Y, so for each Y, you would have just problem when you pick this particular Y, then you have many X, such that this is in the cube. But then if this is just one Y, has measure 0, so you can throw them in this part here, okay? That's okay. But you have many other Y's here for where the corresponding X is just one guy. It's just one X. So this is okay, because the projection of this guy will have just, for each of these other Y's, the thing will be just either empty or it will be 1 point. Okay? So it will have measure 0 in RD1. So you can check that for, so my claim is that for almost, in this situation where you have that your set, if you, doesn't have to be open. If you have a countable intersection of blah, 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 if this set is contained in the boundary of a cube, for almost every Y, okay, the slice will have measure 0 in RD1. So this is my claim. You can check that. They have, and then if the slide has measure 0 in RD1, of course it's measurable and integrable. And all of these things, we have an equality because this is going to be 0, and the integral of f is going to be 0 because my function is the characteristic function of a set of measure 0 in RD. It's in the boundary of a cube. Okay, so you can check the details here. If I have an open cube, and if I have something contained in the boundary of the cube, I'm okay. So the next step is to actually show that, what if I have an open set, almost disjoint finite union of closed cubes? Then I'm okay. So then part C. Part C would be to have if E is the almost disjoint union of closed cubes. Okay. If I have the almost disjoint union of closed cubes, then I'm okay too, right? I'm okay, why? Because each of these closed cubes is an open cube and some parts in the boundary. So each of these closed cubes, I can use the linearity. Take the I can take the closed cube, the open cube, and then its boundaries. So this, a closed cube also is in F by the linearity. I can just add these things up. And when I add these pieces together, I just use, again, the linearity. If I have a finite, F is a finite, almost disjoint union of closed cubes, I'm okay. So just acknowledge that when you have a finite, almost disjoint union of closed cubes, what you do is you are just taking open cubes and pieces of the boundary, and you're taking a finite number of them. So by the property number 1, by step 1, we have agreed that this function here belongs to my class. Okay. So now let me take any open set. How do I do now? So the next step would be to prove for open sets of finite measure. So if E is open of finite measure, I'm also okay. If I have a finite set of finite measure, I'm also okay. How do I do this? Well, you know that we can write my set E. We have seen this construction many times in this class as an almost disjoint union of cubes. I can write E as an almost disjoint union of cubes Qj. The problem here is that this is countable. But no problem, because I just take the truncations of these things. So I take just the function Fn to be the union. I let the set An, A big N, to be the union of the cubes Qj from 1 to n. Okay? So then, of course, the set A1 is contained in A2, is contained in A3, blah, 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 blah. This is going to be contained in E, and it will be E at the limit. You take the characteristic function of A1. It's less than or equal than the characteristic function of A2. And it's going to be equal to the characteristic function of E. But they converge to the characteristic function of E. The characteristic function of each of these cubes, by the previous step, if I have a finite, almost disjoint union of cubes, I'm okay. And here I have, so each of these is in the family, and I have a monotonically increasing limit of functions in the family. By step 2, this guy is in the family too. Okay? So I used here step 2 to conclude that the characteristic function of E belongs to the family. Great. So open sets of finite measure. Remember, all my functions are integrable. Open sets of finite measure are in my family. Finally, let's do it now, what the step 3 wants. Countable intersections of open sets. Countable intersections of open sets. Of finite measure. How do I do this? Countable intersections of open sets. Finite measure. Yes. No, I can actually, Okay, so now let me try to prove the final part, which is just like this. It's a countable intersection of open sets. So I now assume that my E is a countable intersections of open sets, okay, from 1 to infinity. Okay? But I don't know if these guys have finite measure. But since the measure of E is finite, by the definition of the Lebesgue measure, I can place E inside an open set by paying just a little price. So there exists an open set O that contains E such that the measure of O minus E is less than epsilon. We have seen this, right? So in particular, this implies that the measure of O is finite. Okay, so here you have your set E. Okay, you put just inside the little set O. And now you write your E as the, well, E is contained in O, so you write it as O intersection all of these guys. That's the same thing, which is just the intersection of O intersection OK. I just did this, just call this OK tilde, just to guarantee that you have a finite intersection of things which are of finite measure. So now, okay, so these guys now have finite measure. Measure of this OK tilde is finite. Now I want somehow to make this a decreasing sequence. I want somehow to make this a decreasing sequence. So if you start with E being the intersection of OK tilde, each of these guys is open. What you do is you write this, perhaps you let AK, AN being the intersection of OK tilde from K1 to N. Now this sequence AN is a sequence such that A1 contains A2, contains A3, and in the limit this contains E and becomes E. Therefore, and the first one has finite measure because it's just O1. The characteristic function of A1 is bigger or equal than the characteristic function of A2, bigger or equal than this, and this converges to the characteristic function of E. Again, you have a sequence, a monotone sequence of functions in your family. Each of these functions is in my family because these sets AK are intersections of open sets. Hence, they are open sets because it's a finite intersection. So each of them is in the family for part D of step 3 above. And then by step 2, again, I have a monotonically decreasing sequence of sets. Hence, my limit is in the family. So this is why it's important in that step 2 to have either monotonically increasing or monotonically decreasing sequence. This is a space where we use here. OK, so then countable intersection of open sets are in my family. And we have noted that every Lebesgue measurable set is essentially a set like this, right? Every Lebesgue measurable set is essentially a set like this minus a little set of measure 0. So maybe the next step, let me see if I'm correct, is to understand that sets of measure 0. Step 4, if E has measure 0, then characteristic function of E belongs to F. How do we prove this? If a set has measure 0, then it belongs to F. Again, I mean, maybe we can take, maybe what we can do is measure 0, it belongs to F. What do I want to do? Yeah. OK, so this is a bit of a tricky part, but it's not so complicated. So a set of measure 0, I can put my set of measure 0 inside an open set OK, such that the measure of OK minus E, measure of OK is small, right? Any set of measure 0 I can put inside an OK with the measure of this guy small. So I now take K being 1 over K. So I can get E inside a set G, which is just the intersections of all of these OKs, intersection of open sets OK, set like that, with measure of G being 0. Okay. So if a set has measure 0, this is by the definition of, say, the outer measure, if you want. You can put it inside a set OK with the measure of OK minus epsilon, minus E being less than epsilon. So the measure of OK is itself less than epsilon. Then you do this, you can take a finite, a countable intersection, and you can put your set E that has Lebesgue measure 0 inside a set G of that form, inside a set as a countable intersection of open sets. Now, for these sets G, you have seen that the statement of the theorem holds. Okay? You have seen that, we have seen that, that the characteristic function of G belongs to my family F. We have seen that. So now it's just a matter of looking at the statements, because this, let's see, step 1 essentially says that the slice EY is contained in this slice GY, okay? And this slice GY, well, and G has measure 0, okay? So observe that if the measure of G is 0, this final integral here is 0. So this means that this thing here is 0 for almost all Y, okay? So this is a set. So you know that the integral of, in other words, the measure of GY is 0 for almost every Y. So for almost all Y, the measure of this guy is 0. Since this is a guy contained in GY, this is going to be not measurable, and the measure will be 0 too. Okay? So then this implies that the measure of EY will be 0 for almost every Y. So if the measure will be 0, this map, when you integrate, is going to be integrable because it's going to be the 0 function, and this is going to be 0 almost everywhere. Okay? And when you integrate, you get 0. Okay? So you get the statements essentially by looking at this. Okay? So understand the statement for this function G, which is a function, characteristic function of a set of measures 0, where the statements hold. In particular, the last integral is 0, meaning that this inner integral here is 0 for almost every Y. And you conclude that then, since this set is contained in this set, and this set has measure 0 for almost every Y, this will be a measurable set of measure 0. Okay? Because whatever is inside a set of measure 0, here I am in the Lebesgue measure of RD1. Okay? All right, so check. So we are almost there. So we have proved that sets of measure 0 are okay. What else do I have to do? I have to do general sets, right? Step 5 would be if E is a measurable set, then characteristic function of E belongs to F. Yeah, finite measure of E is finite, yes. What I do is the same thing. I can always cover my set E by open sets, OK, paying a very little price. So if I do this, I can put my E inside certain intersections of OKs. Call this set G. Okay, E is inside G. And G minus E, let's call it Z, is G minus E, has measure 0. So in other words, you can write your, what do I want? My G is going to be equal to my E union Z. This is a finite union. Okay, G is from outside E, some piece of measure 0. This is an outside thing. So then this implies that the characteristic function of G is the characteristic function of E plus the characteristic function of Z. This thing here, you already argued that it's in the family. This thing here, you already argued that it's in the family. Linear combination of these two, just a subtraction. This implies that the characteristic function of E is in the family. Okay? So this was perhaps the tricky parts. The two tricky parts of this theorem was to prove the convergence, the monotone convergence, and to prove that countable intersections of open sets are there. So once you have proved this, then you can prove that any measurable set of finite measure belongs to the family, the characteristic function. And the final step is just the conclusion. So any f integrable, f belongs to the family. And we conclude as we argued, because any f integrable you can approach, you can construct a sequence of simple functions, monotonically increasing, phi k simple, finite linear combinations of characteristic functions of sets. And when you are in RD, you can make these sets of finite measure. You can always take, remember the construction. This construction here holds in general measure spaces, but if you are in RD, you can truncate the function phi k on the ball of radius k. And then you increase the radius of the balls and so on. So you make even the characteristic functions of sets that appear being simple. And then it will be each simple function will belong to the family from the linearity and from this step 5, the characteristic function of a single set is. And then the monotone limit, function f, will be in the family because of step 2. Monotone convergence is there. Okay. So this concludes the proof. Nice, right? I just want to conclude the class before we go, mentioning to you this very, very important fact that I cannot. I'll let you do at home the discussion on the general, the Fubini's theorem for general measures. I wrote to you and I'm going to send to you. But just before I depart, let me state a slightly different version of Fubini. So we have seen that when my function f is integrable, when you start with an L1 function, all the slices are almost everywhere integrable in the corresponding spaces, and you can do the integration in any order that you please. Now, there's a different version, which sometimes is referred to as Fubini-Tonelli, or simply Tonelli's theorem. I call everything Fubini's theorem in this sense. Suppose that you have a function that it's non-negative. Start with a non-negative function. Then, let's read it together. For almost every y in RD2, we have the function fy is measurable. In RD1, the function that maps y to this integral of blah, 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 since, of course, it's measurable and non-negative, this is going to be measurable in RD2, and these integrals will be the same. Okay? So the moral is, whenever you start with a non-negative function, you can always interchange the integrals as you please. Whenever working with non-negative functions, you can always interchange the integrals as you please. And the slices are measurable functions. Now, it may happen that the integrals that you exchange here in the end are all infinite. That's okay. But you can exchange them. Okay? It could be that you're having infinity equals to infinity, but you can exchange this and you can do the procedure like this. Okay? So you will use Fubini in two occasions, when you are working with integrable functions or when you're working with non-negative functions. When you are working with non-negative functions, it might be a useful way to prove that something is integrable. So suppose you start with this function f that is non-negative. You don't know that it's integrable. You cannot compute directly, but you can compute like this and then integrate like this. And then you find that it's finite. You know that it's equal, so then this must be finite too. Okay? Because working with non-negative functions, you can always change. Well, the proof of this is actually very simple. You know, you just approximate by below. You just start with the function f, but you consider the function fk of x and y to be just, say, f of x and y if f of xy is less than or equal than k and xy is less than or equal than k2. So if the point is in the ball of radius k and the value of the function is less than k, and 0 otherwise. So consider the truncations of the functions here. So you truncate your function f by the image, by above, and by the domain. Okay? What you will do is you will apply Fubini's theorem to each of these fk's. For each of these fk's, you'll get a slice that is actually integrable, to something that is integrable, and that the integrals converge at the end. And you will apply just the monotone convergence theorem in the appropriate places, right? Because you know that the integral of fk in Rd converges to the integral of f in Rd. These are all finite numbers. Each of k is an integrable function because you construct it. You're letting it be less than k just in the ball of radius k, and 0 otherwise. So it's an integrable function. You can apply Fubini's theorem to each of these guys. When you apply, you'll get the 3 conclusions, and then you will pass the limit when k goes to infinity. The limit of measurable functions will be a measurable function. This will be also a monotone limit of measurable functions will be a measurable function. And the integrals at the end will converge by the monotone convergence theorem. This integral will converge to this. It might be converging to infinity. You don't care, but it will converge. And you can conclude the result for this, okay? Just do these 2 things. I'll let you check the details. It's also written in the notes, and you can work it out at home. Okay, so we're going to finish here the class today and this first part of our course, 12 lectures. You now have a week of break. We're going to meet again on Tuesday, kind of 10 days from now, I guess. So you now have a break of me. If you don't like looking at my face, you have a very good week. Take a look at the notes, study the notes. It's 50-something pages. Do the exercises, discuss with the tutor, discuss with me, and get ready for some action next week, okay? We're going to have our exam a week from now. I am going to email everybody the details. Thank you, everyone. Wow, the camera changed. Okay, so I think the camera was able to move. It was just not picking. Anyway, let's finish here the class today. Apologies for the brief delay.